All right, so we were looking at some examples of different populations and trying to figure out when they're going to meet at the same point. And so, one potential example would be, let's say we have two different bacteria populations. One of them starts with, say, 10,000, and it grows at, let's say, 4% per hour. I don't know if that's realistic. Sounds good enough to me. And let's say another one starts at 6,000 and it grows at, let's just make it grow a little faster, 6% per hour. So we can take that information then and write a couple models and see where they intersect on the graph. And then the question is going to be, how could we find that information out without using a graph? So I'm going to do it in terms of thousands. So 10,000 is my starting amount. It's a bacteria, so it grows continuously. You can think of it as growing continuously. They're dividing every second of every day. So 10,000 of them, I'm using E because it's the continuous growth, raised to the 4% becomes 0.04, and then I'll use X as my variable. You could use T also. So that's the red one. And then the purple one is going to be 6,000 E to the 0.06x. And I'll make it purple so everything matches up beautifully. All right, so if we zoom out here, we can see basically the story that I hope you expected, that the red graph starts out higher because it has 10,000 initially, and then the purple graph starts out lower, but then eventually it catches up. Okay. And if you're using a technology like Desmos, it's super nice. You can just click right on the intersection. If you're using one of the graphing calculators, there's a few more buttons to press, but you can still find the intersection. You just go into the graphing, you type it into y equals, and you graph it, and you just hit second and calculate and find the intersection. Smash the enter key a couple times, you'll get there. But this is just prettier for making a video is all. But the point of this video is not just to show you that I can click on a dot, but it's to show you that you can find that intersection using logs. Just like if you watch the other video, when you have a log equation, an exponential equation that equals a number, you can use a log to find what x value reaches that certain y value. So what I mean, that was stated pretty confusingly. What I mean is, in a previous video, we solved problems like, okay, let's say, when does the red equation reach a height of 20? And we've seen that, okay, then I can divide by 10 on both sides. This is pretty familiar. And then how do I cancel out a base? Okay, a logarithm cancels out a base. So I want to cancel out a base of e. And so then I just have natural log of 2 is 0.04x, and I can then divide by 0.04. So this is the exact value of where my red graph is going to hit a height of 20. So that's just kind of reviewing what we did in another video. By the way, I can prove it to you that I did that correctly if I type y equals 20. If I look at where my red graph hits it, the x value right there is equal to this x value I wrote down there, natural log of 2 over 0.04. And if you still don't believe me, I'll prove it to you. Natural log of 2 over 0.04 shows up, speed that up a little bit, 17.3, exactly like the point of intersection right there. You might be wondering, though, how can we solve an equation where we have exponentials on both sides? And so that's the different piece I'm trying to get here in this equation. So in this video. So let's take our red equation, 10e to the 0.04x, and let's figure out when that's equal to our purple equation, 6,000, so 6e to the 0.06x. In the previous example, in the black example, I divided both sides by 10 to try to get my e by itself. The tricky thing here is I've got e on both sides. So what I'm going to do first is divide both sides by e. And I'm going to choose the e that has a smaller exponent. You don't have to. You could divide by the bigger exponent also. I just like to divide by the smaller exponent. So I'm going to divide both sides here by e to the 0.04x. If you divide something by itself, it crosses out. So like in this example here that I did earlier, 10 divided by 10 crossed out the 10s from the problem. My new example, e to the 0.04x, crosses out with the other e to the 0.04x. So now I have 10 equals 6, and I can't cross out those e's because the exponents don't match up. The top exponent is bigger than the bottom exponent. If you think back to when you studied exponents, you learned how to do problems like this: x to the fifth divided by x squared. Think about how that works out. It ends up being x to the third because the 5x's on top cross off 2 of the x's on the bottom, and you have 3 left over. In general, anytime you have a top power and you have a bottom power, you can subtract top minus bottom. And I'm going to use that idea here. My top power is 6%, and my bottom power is 4%, so the difference in their growth rates is 2%. Okay, so that's the idea here, is that we're dividing to figure out how quickly they are growing closer together. They are growing closer together at a 2% rate because the bottom curve is growing 2% faster than the top curve. It's just like when we were finding growth rates, we divided our two values to find the growth rate. Here we're dividing our two functions to find the growth rate of how quickly they come together. Well, now what I have left over, this equation right here, is going to be a repeat of what I did down here in the bottom left of the screen. So really, that first step was the only new piece. 10 divided by 6 is, well, what is that? I don't know, 5/3. So 5/3, or I could say 1 2/3. If you really like decimals, you could do decimals. Now I do natural log of both sides because that cancels out the base. And last, I divide by 2%. And that's going to be my x value. And so I know that this x value right here is equal to where my two curves cross, 25.5. I will prove it to you if you somehow don't believe me. 5/3 goes there, 0.02 goes there, 25.5, 25.5. So there you go. If you are in a situation where you've got two exponential equations, you can set them equal to each other to find the point of intersection. Just like when you did systems of lines, you set them equal to find the point of intersection. When you did systems of lines, you wanted to get all your x's on one side and your numbers on the other, and you usually did that by adding and subtracting. And that's because linear means you're adding and subtracting. When you're doing exponents, you do multiplying and dividing to get everything on the same side, and then use a log to solve. So please comment. Let me know if there's anything confusing or if you have more examples you'd like. Thank you.